Hello, wonderful people. Here we are at the beginning of a new chapter, chapter 44. On this slide, I am the purple, pink, and white text reader. There it is, chapter 14, Satellite Motion. If you drop a stone, it will fall a straight line path to the ground below. If you move your hand horizontally as you drop the stone, it will follow a curved path to the ground. If you move your hand faster, the stone will land further away and the curvature of the path will be less pronounced. What would happen if the curvature of the path matched the curvature of the earth? The answer is simple enough. Without air resistance, and you know how much we love to ignore air resistance here in physics class, the answer is simple enough. You'd have an Earth satellite. What would happen if the curvature of the path matched the curvature of the Earth? You'd have an Earth satellite. Do you remember this picture? This was drawn by Isaac Newton himself. Where's my pointer? There's the top of the mountain. You throw the cannonball that hard, then harder, then harder, then hard enough. It makes a complete circle around the Earth and hits you in the back of the head 84 minutes later. Now, you could do this if you had, one, a mountain high enough, not too hard to find. Two, you would have to take away all the air off the Earth. That would be hard to do. And three, you'd have to throw it so hard, just crazy hard. But you could do this. Now, the main trick is to get above the Earth's atmosphere. So that's up here. Up there, if you're above the Earth's atmosphere, you need to go, 18,000 miles per hour or something in order to circle the Earth. And if you go higher and higher and higher and higher, yep, we've talked about this a few times now. There's the cannon on top of the mountain. There's the North Pole, so that cannon's on the equator and it's going around the equator. This is kind of a neat trick. There's the path where it follows a perfect circle. So the radius is constant from the center of the Earth to the path of the circle. Now, if it's a little slower, it will dip down closer on the far side, and that's an ellipse. Also, if you shoot it a little faster, it will go out past the circle. So now it's further out here, and then it falls back into the cannon. It still hits you in the back of the head. So you've got an ellipse that's less than a circle. You've got an ellipse that's greater than a circle. And then if you fire it at exactly the right number, so that the velocity is exactly the perfect speed, it will escape the Earth and it will follow a parabola. Now, if it's a little bit slow, it will come back into an ellipse. And if it's a little bit faster, it will follow a path called the hyperbola. Now, if you know the difference between a hyperbola, parabola, and ellipse from math class, great. If not, don't worry about it. I'm not that worried about it. I just thought if you know these things, it would be neat to see it right here, right now. Now, both a hyperbola and a parabola mean that the cannonball escapes the Earth. It does not orbit. It leaves the Earth and goes out past the solar system, past the galaxy, and goes on outward forever and ever. The end.